In today's video, we will cover Cantor's theorem. Cantor's theorem states that for any set A, whether it's a finite set or infinite set, the cardinality of A is strictly less than the cardinality of the power set of A. So basically, this is a statement about the sizes of two sets. The size of set A is strictly less than the size of the power set of A. Let's begin by recalling what the power set of A is. So given a set A, we define its power set, which is denoted by this P of A, to be the set of all subsets of A. So in mathematical terms, the power set of A is just a set whose elements happens to be sets themselves. Specifically, they're just all subsets of A. So as an example, if A happens to be the set with two elements, just I and J, then the power set of A is going to be all subsets of I and J. So we're going to have the singleton I, we're going to have the singleton J, we're going to have the set A itself, and then the empty set is a subset of all sets, so that's also here. In general, if A is a finite set with n elements, then the power set of A has 2 to the n elements. Now you can prove this using induction, or you can also take a combinatorial approach where if you have a set with n elements and you're trying to build a subset out of those n elements, then you have to make a decision, yes or no, for each of those n elements. So it's basically 2 options times 2 options times 2 options n times. So that gives you 2 to the power of n. And then we can show that n is strictly less than 2 to the power of n using induction, and then this basically proves Cantor's theorem for the finite case when A happens to be a finite set. But actually, Cantor's theorem holds for any set, for infinite sets as well. As another example, if A happens to be the set of natural numbers, then the power set of the natural numbers is going to be a set of sets. And so one element or one member of this set is the set of even numbers. And notice I'm using element of, not subset. So this is a member of this power set of natural numbers. Another example would be the set that has 9, 99, 999, and so on. So this would be another element of the power set of the natural numbers. We can also have finite subsets. So for example, 5 and 25. This set is a subset of the natural numbers, and therefore it must be an element of the power set of the natural numbers. We can also have singletons like the singleton 1, the singleton 2, and so on. These are all elements of the power set of the natural numbers. And of course, the empty set and the set itself are always subsets of the original set, and so therefore they are also in the power set. And here's a non-example where we have a half and a third, and so these are not elements of the natural numbers, and so therefore, although this is a set of numbers, it's not a subset of the natural numbers, and so therefore it cannot be an element of the power set of the natural numbers. Okay, now let's jump into the proof of Cantor's theorem. We begin by showing a looser condition, that is, we will show that the cardinality of A is less than or equal to the cardinality of the power set of A. And to do this, we will create an injective map. Let's call it F, that goes from A to the power set of A, and it's very simple. It just maps the element A to the singleton A. And to make this map a little bit more concrete, let's consider the example up here where A happens to be the set of natural numbers. Then F is going to be mapping all the natural numbers into the power set of natural numbers. And so if you were to illustrate this, what's happening here is 1 is getting mapped to the singleton 1, 2 is getting mapped to the singleton 2, 98 is getting mapped to the singleton 98, and so on. So we can see all the natural numbers are getting mapped onto something in our codomain. But there are elements in our codomain that don't have a preimage. For example, the set 1, 2, the empty set likewise has no preimage. And so this is just an illustration to show that the cardinality of n is less than or equal to the cardinality of the power set of n. Now we can show that the cardinality of A is strictly less than the cardinality of the power set of A. And to do this, we will argue by contradiction. We will suppose that the cardinality of A is equal to the cardinality of the power set of A. Well, if that's the case, then there must be a bijection between these two sets. So there exists a bijective function, let's call it f, that maps A onto the power set of A. And now let's define the following set. Okay, so we're going to define a set X, and this set X is going to have all members of A such that A is not in its image. Okay, so this set looks a little bit confusing, but let's break it down with an example. Let's take the same example where A is the set of natural numbers. Okay, and here's our function f. Let's suppose that 1 gets mapped onto the singleton 1, similar to what we had up here. So you can see that 1 is getting mapped onto 1, which is f of 1. In this case, 1 shows up in its image. So therefore, we cannot collect it in this set, because this set, the condition is that A must not show up in its image. Over here, 1 is showing up in its image, so therefore 1 is not in X. Let's take a look at another example. Let's suppose that 2 was getting mapped to the set 1, 98. So this is just an example of a function f. Let's suppose that 2 was getting mapped onto 1, 98. This is f of 2. Well, you can see that 2 does not show up in its image, right? So therefore, we will collect 2. 2 will be an element of X. So that's the way you want to think about this set. This is a set of elements from A, or in our example, it's a set of just natural numbers. These are natural numbers that do not show up in their image under F. Okay, so the set X, by construction, is just a set of members from A. So by definition, it's a subset of A. Well, if X is a subset of A, then it must be an element of the power set of A, because the power set of A is the set of all subsets of A, and if X happens to be a subset of A, then it must be a member of the power set of A. Okay, well, since F happens to be bijective, in particular it happens to be surjective or an onto function, that means X must be the image of some element in A, right? There must be some input in A that gets mapped onto this set X. So therefore, let's suppose there is some Y in A that gets mapped onto X. So X is equal to f of Y for some Y in A. Finally, Y should either be an element of X or it should not be an element of X. Remember that Y is just an element of A, and X happens to be a subset of A, right? X happens to be a subset of A. So the question we're asking is Y an element of this subset or not an element of this subset? Okay, well, let's suppose Y is an element of X. Okay, then what does that mean? Well, if it's an element of X, then Y cannot be in its image. So Y cannot be in its image. But what is f of Y? Well, we define that to be X, right? So Y is not an element of X. So we started with Y is an element of X, and we ended up with Y is not an element of X. So that is a contradiction. Now let's check the other case. Let's suppose that Y is not an element of the set X. Then that means that Y does not satisfy this condition. Well, if it does not satisfy this condition, then Y must be an element of its image. So that's what I've written over here. Y is an element of its image. And what is f of Y? Well, again, that happens to be X. So we started with Y is not an element of X, but we ended up with Y is an element of X. So we got a contradiction again. So this is a problem, right? Because like I said, Y is an element of A, right? And X happens to be a subset of A. So Y should either be in this subset or it should not be in this subset. And so we've gotten a paradox here. When we suppose Y is in X, we get a contradiction. When we suppose Y is not in X, we also get a contradiction. So we're not sure which one it is. And the reason we got this contradiction is because of this assumption that we assumed there is a bijection between A and the power set of A. So this completes the proof of Cantor's theorem, which shows that the cardinality of A is strictly less than the cardinality of the power set of A. Lastly, I would like to end with some consequences of Cantor's theorem. So Cantor's theorem gives us a way to generate larger and larger sets. And this gets very interesting when we look at infinite sets. So we start with the set of real numbers, and then we take the power set of that gives us an even larger set. then we can take the power set of the real numbers and get an even larger set. And so this is pretty cool. And so this is pretty cool because the set of natural numbers is a special type of infinity called countable infinity, where we can actually enumerate or list out the numbers in n. Whereas the set of real numbers, although it's an infinite set as well, is actually a much larger infinity. We're unable to enumerate or list out the real numbers. And so I would like to end with the following statement, the continuum hypothesis. So the continuum hypothesis states there is no set A whose cardinality is in between the naturals and the reals. And it turns out that this statement is both true and false. Specifically, in the 1900s, two mathematicians, Kurt Gödel and Paul Cohen, showed that it's impossible to prove this statement from the axioms of set theory, and it's also impossible to disprove this statement from the axioms of set theory. So this is a mathematical statement that shows the limitations of axiomatic systems. This brings us to the end of today's video, where we covered the proof of Cantor's theorem. I hope you found the explanation helpful.